Welcome to this video on solving right triangles. A right triangle is a triangle with a 90-degree angle. You see the little box in the triangle there. That represents perpendicular line segments and therefore a 90-degree angle. Suppose I wanted to solve a right triangle with a 25-degree angle in it. To solve a right triangle means to find all of the missing sides and angles. You're unlikely to find this problem in a mathematics course, however, because it turns out there are infinitely many triangles with right triangles with a 25-degree angle in them. And in some sense, I haven't been given enough information to narrow this down to a single triangle. So in a math course, we might say not enough information given. That just means there's infinitely many situations that match this description. Let's say we were given this right triangle and asked to solve it. Again, to solve it would mean to find all the missing angles. But this turns out to be an unsolvable problem in a sense. And I'll show you why that is. If we were to create a right triangle with a 57-degree angle and a side length of 8, the other side would end up being about 9.5. Another reason this may be unsolvable is if we were given a right triangle with side lengths 10 and 8 as shown, the angle would turn out to be 53 degrees and not 57. Or if we wanted to find a right triangle with a side length of 10 and an angle of 57, the other side would end up to be about 8.4. So it turns out that this problem, as stated, doesn't exist in the sense that there is no right triangle in the physical real world that matches all of these descriptions. You're unlikely to run into these in mathematics courses as well, but it's worth pointing out that if we specify too much information about a triangle, then there won't be a triangle that's buildable to those specifications. So on the left side of your screen, we were given one numerical piece of information, and that didn't seem to be enough to narrow it down to a single answer. Whereas on the right side of your screen, we were given 3 pieces of information, which seemed to be, in some sense, too much, and there were too many constraints there, and we couldn't solve for the right triangle. What you're most likely to encounter in a mathematics course is a right triangle where 2 numbers are given. And when that's the case, typically, there is exactly one triangle that matches that description. And that's the focus of this video here today. When we've given you just the right amount of information to narrow it down to a single triangle, but left enough information for you to solve for, this is what we find in mathematics courses. And in this video, you'll see the techniques to find all of the missing sides and angles. I'm not explaining where those came from yet. That's the purpose of this video. Before we go on to our examples, something worth thinking about. The figures or diagrams that we draw are typically not to scale. Even when we fail to state that they're not to scale, it's understood that the diagrams we draw do not necessarily look the way they would look in real life if we were to build this triangle. There's 2 reasons for that. One, sometimes math teachers don't feel like taking the extra time to draw things to scale, so we simply don't bother. But there's a different and probably more significant reason. When we get into higher mathematics, you'll be looking at triangles that represent figures in motion that are changing. And when things are in motion or changing as a function of time, you can't draw them to scale, except to draw a video of them, of course. And so diagrams tend not to be to scale typically because in higher mathematics, they represent dynamic situations that can't be drawn to scale at any one moment. And just to say what I mean about not drawn to scale, if this side length were 4.2, then this side length clearly wouldn't be 12.3, because that would be about triple the size, but clearly that's not triple the size in the physical world. I've drawn this diagram to scale just to give you a better sense of what I mean by drawn to scale. But again, don't expect diagrams to be drawn to scale in this video or in your mathematics courses. So now let's begin the process of solving right triangles. and discuss how sines, cosines, and tangents, trigonometric functions, can be used to do this. Here's an example. Suppose I wanted to solve this right triangle. That would mean to find all of the missing angles and sides. Well, we're not quite ready to show the mechanics of this process yet, so let's develop some ideas first. One thing that somebody had creative thought on centuries ago was that we could compare this triangle to a similar triangle, a smaller version of this triangle, condensed inside the unit circle. Now, the triangle we're trying to solve is much bigger than the one in the unit circle, because the unit circle has a radius of 1. Now, why was this a clever idea, to compare our triangle to a smaller version of itself crammed inside the unit circle? Well, the reason why this would have been such a great idea is because they had already built up this whole mechanism of sines and cosines. Remember, the cosine and sine are the x and y coordinates of a point on the unit circle corresponding to a certain angle. Therefore, if we cram this larger triangle from the top of the page into the unit circle, still having a 35-degree angle, then we'll have a point on the unit circle, you'll see it as a red dot, that corresponds to that 35-degree angle, and we know the x and y coordinates of that point if we can compute the sine and cosine of 35. So then the logic went like this. If the triangle on top has a hypotenuse of 5.1, and the triangle on the bottom in the unit circle has a hypotenuse, or in this case radius of 1, then the triangle on top must be 5.1 times larger on all the side lengths, not just the hypotenuses compared. And therefore, someone figured that we could just multiply the legs of the smaller right triangle by 5.1 and get the legs of the larger right triangle. Clever logic. Now, if you have means to compute the sine and the cosine of 35 degrees, which nowadays we do by calculator, and back then they did by other means, then you could compute those side lengths and therefore solve for most of this right triangle. Now, I'm not going to finish solving the triangle, but the purpose here was just to show that originally they compared right triangles to smaller versions of themselves or similar triangles within the unit circle. And the unit circle was a great strategy for comparison for solving even triangles that didn't fit inside the unit circle. But then some mathematicians had a better idea. They sort of said to themselves, why don't we generalize this idea? Not just for 35-degree angles, but what if in general we just had some other angle? Call it theta, because it could really represent anything between 0 and 90 in the first quadrant here in this picture. So for any given angle theta, we could compute the sine and cosine of theta. In other words, we could examine a shrunken down version of any triangle we wanted to solve by placing it, a similar version of itself, in the unit circle. So they decided to come up with some formulas and create names for the side length. The side length names that they created for these formulas are hypotenuse, opposite, and adjacent. The hypotenuse is the side of the right triangle that does not touch the 90. The opposite is the leg of the right triangle that does not touch the angle in question, in this case theta. And the adjacent is the leg of the right triangle that does touch the angle in question, or is adjacent to or next to theta. Let me put abbreviations for these names so we have less to write. And so went the logic. Watch this. Mathematicians said to themselves, hey, we could set up proportions, because if these two triangles are similar or proportional to one another, then we could simply make an equation out of two ratios. For example, we could say the pink is to the blue as the pink is to the blue here. In other words, we could set up this ratio. Well, the sine of theta divided by 1 is the sine of theta. So it was determined that we could always use the equation sine of theta equals opposite divided by hypotenuse for any triangle. Likewise, we could say the green is to the blue as the green is to the blue. And that's exactly what they did, coming up with this proportion. Rewriting it, given that anything divided by 1 is itself, gives us another proportion from trigonometry and right triangles. And the last thing they considered is let's compare the pink to the green here as the pink compares to the green here, coming up with this ratio. Excuse me, proportion technically is when two ratios equal each other. Well, given that the sine of theta divided by the cosine of theta is the same as the tangent theta, that gave us our third main trigonometric proportion that we can use in dealing with right triangles. And the idea here of all of this was the following. What if we don't want to compare everything to the unit circle every single time? What if our triangle does not have a hypotenuse of 1? Well then, we can use these ratios, which are based on the unit circle, without actually using or introducing the unit circle into any problem. So we won't use the unit circle in this video, but this shows an interesting historical reference of how the unit circle was used to create these ratios. And now that they're created, we're free to use them in any right triangles we'd like, whether or not the hypotenuse is 1. And these will be the basis as we go further in this video. So let's examine our first actual example where we're going to completely solve a right triangle. Suppose we're given this right triangle and asked to solve. That means that we need to find every missing angle and side that's not already mentioned. Now, does such a right triangle even exist? And if so, is there more than one right triangle that matches this description? Well, generally speaking, in a mathematics course, when you're asked to solve a right triangle, the assumption is that there's only one right triangle that has a 20-degree angle and a 15 side length as shown, and we're therefore supposed to uniquely identify all of the remaining sides and angles. So let me outline a procedure now that we're looking at our first real example that you can follow when you're solving a right triangle. Step 1, name everything you don't know. You're not required to use Greek letters for angles, but it's something I often do. So I've named everything that I don't know here. And that's what I need to find to, quote, solve this right triangle. Next, I like to label the sides as opposite, adjacent, or hypotenuse so that I can use my trigonometric proportions that we developed earlier. Well, the hypotenuse is the side that's not touching the right angle, so clearly the hypotenuse would be x in this particular case. But when it comes to opposite and adjacent, it really depends on the angle that you're referencing. For example, if the opposite is the leg of the right triangle not touching the acute angle, then we could call y here the opposite of theta, because y is the leg not involved in angle theta. But we could also call the 15 as being the opposite of the 20-degree angle. So in some sense, both legs are opposites, but opposite of what is the question? So one leg here is the opposite of the 20-degree angle, and one leg is the opposite of theta. In a similar fashion, if the adjacent is the leg that is involved or touching the angle, then both legs are adjacent. The 15 is adjacent to the theta, and the y is adjacent to the 20. So when you label your sides, you really have two opposites and two adjacents because those two leg names refer to being opposite or adjacent to a particular acute angle. And the acute angles here are theta and 20. Acute, by the way, meaning less than 90. Next, what I like to do is write out all possible equations for right triangles. First, notice in reference to the angle theta, I could write out our three basic trigonometric proportions. And I could take the x and the y and the 15, which are my side lengths, and plug them in. But I could similarly make a same set of equations using the 20-degree angle. And this raises an interesting question. Should we use theta as our angle of reference, or should we use 20? Well, right now I'm not focusing on that so much. I'm simply saying that we could actually make 6 trigonometric ratio or trigonometric proportions here, because we can make 3 out of the 20-degree angle and 3 out of the theta angle. There's also something that's not a trigonometric proportion called the Pythagorean theorem, which by now I'm sure you're familiar with. But you can also make a Pythagorean equation out of any right triangle. That's just leg squared plus leg squared equals hypotenuse squared. And finally, there's another equation that comes to right triangles, and that is that the angles must always add up to 180. That's beyond just a right triangle fact. That's an all triangle fact. So it turns out there are a total of 8 equations that you can make out of every right triangle. Now, when you're solving problems like this, do you want to write out 8 equations? Not necessarily, but I'm going to do that just to show a point here, that some people may like to start out writing all 8 of them. Before we begin, let's look at the names opposite, hypotenuse, and adjacent and replace those with x, y, and 15 in this case. And so what I've done here is I've created 8 equations. And you might be thinking, I don't want to write out 8 equations when I'm trying to solve a right triangle. Well, I don't either. But sometimes, especially if you're new to this process, you'll have to write out all 8 of them and use the process of elimination to decide which ones aren't particularly helpful. One thing that I think is very useful is, in an effort to solve the equations here, you might want to discard any of them that have 2 or more unknowns in them. Take a moment, even pause the video if you need to convince yourself that all the equations here shown in pink have 2 unknown quantities in them. Now, while all of these equations are mathematically correct, none of them are particularly useful. And so, I'm going to discard them. And now my 8 equations have reduced down to 3. And I can use these equations now to solve for x, y, and theta. Now, the more advanced or experienced right triangle solvers among us won't write out all 8 of them. There are many people, and I'd like for you to get to this point at some point in time. Many people can just write out these 3 equations just by looking at the picture and not particularly have to write out all 8 of them, and that's fine. So you'll have to decide, are you a person who can look at a diagram and create only the equations that are the most relevant? Or are you a person who's going to have to write out all 8 of them to determine which are the most relevant and solvable? That I'll leave to you. But now let's embark upon the process of actually solving for x, y, and theta. Let's start with x. Sorry, let's start with theta. Theta is the easiest one to find here. You can simply subtract 20 and 90 from both sides and get theta. Theta is a 70-degree angle. Now, for the purposes of sine, or the sine equation, you might want to write sine of 20 as sine of 20 over 1. You don't have to, but it leads to a nice visual trick where you can cross multiply for proportion solving. And now, in order to solve for x, I simply divide both sides by the sine of 20. And the sine of 20 is something I can compute on a calculator. It's a decimal. I've got a calculator in my hand right now. The sine of 20 degrees works out to about 0.34-ish. 15 divided by 0.34 roughly is about 43.9. And so now I have an approximation for x. Now let's solve for y. You don't have to express the tangent of 20 as the tangent over 1, but it's again a nice visual trick to cross multiply, divide by the tangent of 20, and just figure out what the tangent of 20 is as a decimal. I'm holding a calculator right now. The tangent of 20 is about 0.36. 15 divided by 0.36 is about 41.2, and now I've solved for y. So I've solved this triangle. By the way, before we go on to any further examples, there's something I'd like to note here. Our three trigonometric ratios that are turned into these proportions here, somebody, years and years ago, for whatever strange reason, was having trouble memorizing these, I suppose. And so they looked at the first letter of each of the functions and words in the problem. And they took those 9 letters and they made a fake word, sohcahtoa. This fake word is a good way to remember the equations if you ever get stuck and can't remember one of them. Now, whenever you see or hear a math teacher saying, let's use sohcahtoa to solve this problem, what they're really saying is let's use a trigonometric proportion, or one of the three, to solve this problem. And I may do that in the rest of this video as well and say, using sohcahtoa, the following must be true. So keep your ears out for that word. Here's another example. So, in order to solve for this right triangle, which means to find all the missing legs and angles, I'm going to put in names. Again, I use Greek letters. We'll use beta here to represent angles. You don't have to do that, of course. And really, it doesn't matter what you call anything. To solve a right triangle means to find all the missing legs and, missing sides and angles. And so what you name them is irrelevant. But here are my names. So I like to label my sides next. This is the hypotenuse. Now, as far as opposites go, I have 2 opposites. I have one leg opposite the beta and one leg opposite of the 43. And for adjacents, I have one leg adjacent to the 43 and one leg adjacent to the beta. Now, one thing that I've noticed is that if you want to write out all 8 equations for a right triangle, you can, and you'll need all of this information. But generally speaking, I try not to write out 8 equations. And I'm not going to use beta as my angle of reference here because it probably won't lead to anything. How do I know that? Experience. How would you know that? Just an intuition, I suppose. You could always write out all 8 equations and you'd find a lot of unuseful ones there. But nonetheless, let's continue. I want to show you a quick example of how you'll know if you write an equation that's useless. Let's say we decided to use the tangent is the opposite over the adjacent in reference to the 43-degree angle. Now, this is a true mathematical statement, but notice it has 2 unknowns in it. So when you're writing out equations for a right triangle, if you write one that has 2 unknowns in it, you're not wrong. You just haven't written anything particularly useful. And therefore, I wouldn't go down that path. Well, out of all 8 equations, one of them that's going to be particularly helpful is to use the sign in reference to the 43-degree angle. Because if I set up the sign is the opposite over the hypotenuse, essentially using sohcahtoa here, then I have an equation that has 1 unknown in it. And that's what we're looking for when we're solving right triangles. Now I can simply cross multiply, reach for a calculator, find out that the sine of 43 is, typing it in now, sine of 43 is about 0.68. 10 times 0.68 is about 6.8. And now I have an approximation for m. Let's continue to solve for another variable. Out of all 8 equations, setting up a cosine in reference to 43 is also helpful. There's no way you would know that, You really have to do a lot of trial and error here to find useful equations. But you'll notice that the cosine of 43 being adjacent over hypotenuse, again using SOHCAHTOA here, will lead to an equation that has a single unknown in it. And that, again, is easy to solve. Set up a proportion, cross multiply, get a calculator, find out the cosine of 43, and whatever that is, multiply it by 10. And that's precisely what I did here. And now I know the value of k. Finding the value of beta, our remaining unknown, is pretty easy. Again, using the fact that the angles of a triangle must always add to 180 allows me to solve for beta. And now I've solved this triangle. Here's an example that's a little different in the sense that there are no known angles other than the 90, of course. But these are still doable in a slightly different way, still using the 8 equations. So I'm going to label all the angles and the side I don't know. So I've labeled them with theta, alpha as my angles, and L as my length of my hypotenuse. So let's name the sides. Actually, no, let's use the Pythagorean theorem here. Now, out of all 8 equations, you haven't seen me use the Pythagorean theorem much here, but it's particularly useful in this case because it's going to enable me to solve for L. So I took the radical of both sides, and I used a calculator. The work isn't shown here, but what I did was I got 4 squared is 16, and 6.2 squared is whatever that was. I added those together, took the positive square root of that, and I got 7.4. The Pythagorean theorem isn't always a helpful equation, but in this case it came in real handy. Now let's set up a tangent equation. Why did I choose tangent and not sine or cosine? I can't answer that directly, but what I can say is, if you're unsure, write out all 8 equations, and you'll see this among your 8, and you'll recognize it as an equation that only has one unknown in it. So there's no particular way to know I should use tangent in this problem, or I should use sine in this problem. But after a while, you start to get an intuition about it. To develop that intuition, write out all 8 equations. And what you'll find is you'll catch yourself about to write an equation with 2 unknowns, and then you won't write it at all. And pretty soon you get a pretty good intuition, like, oh, I should use tangent here. Okay, well, let's go about the business of solving. 6.2 divided by 4 is 1.55. But I have to solve for theta here. To dispel a quick, very wrong thing that I've heard so many students say here. I've heard students say, let's divide both sides by tangent. Well, tangent isn't a number or an algebraic quantity, and this isn't tangent times theta, it's the tangent of theta. So if your brain said, divide by tangent, that doesn't even mean anything. So then if we can't, quote, divide by tangent, which doesn't make any sense, how do we solve for theta? Well, what you can do here is use an inverse trigonometric function to find theta. Because it turns out I can go from the tangent of theta to theta by just applying the inverse tangent to both sides of the equation. Now this comes with a warning. In general, it is not correct to say if the tangent of theta is 1.55, that theta must be the inverse tangent of 1.55. That is not generally allowed, to just simply bring a tangent over as an inverse tangent. That's an illegal math move in general. After all, you may recall, depending on your trigonometric knowledge, you may recall that the inverse tangent is that specific angle between negative pi over 2 and pi over 2, or between negative 90 degrees and 90 degrees, which has a particular tangent value. So it is not generally acceptable to go from the tangent equation to the inverse tangent equation here. So if it's not acceptable, why am I accepting it? Well, it turns out, if you happen to know that theta is an angle between 0 and 90, or think of it as an angle in quadrant 1 in the unit circle sense, if theta is an angle between 0 and 90, and you know that to be a fact, then this is a valid move to simply move the tangent over to the other side. Well, look at the diagram at the top. Theta is an acute angle in this triangle. Of course it's between 0 and 90. Every non-90 degree angle in a right triangle, is an acute angle between 0 and 90. And so, while it is not generally acceptable to simply throw the tangent to the other side of the equation as an inverse tangent, it is acceptable if you know that theta is between 0 and 90, which of course we do in this case. At this point, all you have to do is reach for a calculator. Depending on your calculator, make sure that you're in degree mode, unless your teacher wants the answer in radians. And putting my calculator in degree mode, typing in inverse tangent of 1.55, lets me know that theta is approximately 57 degrees. It was actually a decimal angle, but it's traditional to round angles to the nearest degree. So now I know approximately what theta is. So what unknown is left? I still don't know alpha. Could I use tangent in a similar way to find alpha? I could. Could I use sine or cosine in a similar way to find alpha? Well, I could now that I know what L is. But why do any of that when I can simply use the angles must add to 180 rule to find alpha? And that led me to approximately 33 degrees. Now here's our last example. Suppose we're trying to solve this triangle. Again, label all the sides and angles you don't know. So I've got delta, beta, and c. I decided here again to start with the Pythagorean theorem. There's no rule that says I have to. I just noticed that if I start with the Pythagorean theorem, I'll be able to find out what c is. So I used the Pythagorean theorem, and I found out that c is 3. Okay, next I decided to make an equation out of cosine. Is it mandatory that I use cosine at this point? No, not at all. Could I have used sine of delta? Sure, now that I know that c is 3, that would have been a productive endeavor as well. There are many, many ways to go about these. One should never feel like they have to follow any particular procedure. Just remember, there's 8 equations that apply to right triangles. And your job is to either A, write out all 8 of them, or B, to sort of think it through so you don't have to write them all out. Either one is fine. But among the 8 equations is this one, and notice it only has one unknown, and that's delta. So let's continue solving for delta. 4 divided by 5 is 0.8. Now, am I allowed to simply go to the inverse cosine version of this equation? Not in general, but if I know that delta is an angle between 0 and 90, then yes, I am allowed to do that. Well, of course, I know that because it's an acute angle in a right triangle, so of course it's between 0 and 90. So typing that into your calculator, assuming you're in degree mode, will give you a decimal, but that approximates to 37 degrees. And now that I know delta, how do I find beta? Well, there are many equations out of the 8 that would allow me to find beta now, the simplest of which is that the angles must add up to 180, and using that, I now know beta. And that completes this lesson. Thank you so much for watching.